Hey everyone, Max here. Today I'm just going to be talking about proportion testing. So we're going to be thinking about population proportions. Specifically, how these are important, where they come from, and why we use them. And just a nice overview and how we're going to end up getting our test statistic. Okay. So specifically in the past, sorry about that. In the past, we've used, say, x is distributed as a normal random variable of mu sigma, y distributed as, say, a t with degrees of freedom nu, right? And we figured out how to use these, okay? So we know how to use these. And these are specifically, and I've mentioned this before in my class, but we've talked about how these are continuous. Random variables. Specifically, you can track things like height, you can do money, you can do, say, test scores, etc. Okay. But now it comes down to, what if we wanted to use something like a binary random variable? And by that, I mean, what if we wanted to do something more discrete? So, okay. So, what if we wanted to use a discrete random variable? So instead of our sample space omega being equal to the real numbers, so we don't have this, what if omega is equal to, say, heads or tails? Or omega is equal to agree, disagree? Or omega is equal to yes, no. So what do we do in all these cases? Right now, we don't necessarily have the tools for it. We have the scaffolding for the tools, but we haven't necessarily put them all in place to really see how they're going to work in the larger picture. So what we're going to do is, I'm going to frame this in the context of heads or tails, because I think it's the easiest to conceptualize. But you can always actually think about this in terms of any binary response. And by binary response, I just mean, so binary response. By this is a non-technical term, but I'm just going to let you know how I'm using it. This binary response is there's only two answers. And whenever you have an answer, it's always going to be from your sample space, because it's going to be binary. Binary coming from this idea of just zeros and ones. Okay. So when we start thinking about these binary questions, a common one is if I flip a coin. This can be modeled by something we call a Bernoulli random variable. And you usually put Bernoulli P, where P is the proportion. Specifically, a Bernoulli random variable can model, commonly people just think of it, model a coin flip. And the expectation of a Bernoulli random variable, say x is distributed as, we'll just draw a little arrow so I don't have to write this whole thing up. And so the expectation of this is going to be with the expectation of x being p. And remember, the expectation is just a fancy word for the mean. So this p right here, in the example of a coin flip, right, is going to be 1/2 if we're modeling a fair coin. The theoretical mean of a fair coin would be 1/2. So this proportion, if we're, say, testing a bunch of coins, or if we're asking people whether or not they agree or disagree, is really going to be what we're after. So we're after this sample mean. And if you recall this normal random variable mu sigma, we were always trying to estimate mu. That's why we had mu naught, we had all sorts of speculations about mu, and we had the sample mean. So when you also find, and on that note of the sample mean, when you compute the sample mean, you'll actually be computing what we call a p hat, okay? So p hat is the estimated mean from 1/n sum of xi. Okay, and this is what's going to happen. This is what you'll end up finding. And so when I denote, say, like a p naught, this is really equivalent to our mu naught. And we're going to be talking about these p's and these proportions. You may be thinking, oh, we just went from sample means to coin flips. How did this happen? We've actually haven't changed what we're studying. We're actually just changing what the random variable looks like. We're still after the mean. We're still looking for the same thing. We're still going to use the same formula, but we're just changing what our random variable looks like. And so when we go back to the sampling distribution, right, I believe it was in chapter 10, sampling distribution. We have the x bar going to be distributed as n mu sigma over root, right? So if we want to change what this thing looks like, and keeping in mind this sigma over square root of n, this mu, and remember I had talked in class about how z, when we're doing the z test of it being x bar minus mu naught over sigma over root n, and I drew this whole parallel between the sampling distribution and a z-score and everything. We're now going to think about a z-score, and I'll talk about in a minute why it's going to be a z, but we'll talk about this. Now, this x bar, when we have a Bernoulli, okay, let's say use a Bernoulli now. I don't like that. Let's say use a Bernoulli, so using Bernoulli random variable. This x bar is going to be replaced with a p hat, okay? Minus, I'm going to put a p naught, okay? And now we need what the standard deviation of this thing is going to be. Now the standard deviation of a Bernoulli random variable, I won't go through the entire derivation, but the standard deviation of a Bernoulli random variable, what we call the variance, so let's have this be x, so x is distributed as that. So the variance, which is essentially a theoretical standard deviation, again, this isn't something you need to memorize, this variance of x part, but this variance of x is defined to be pq, where q is equal to 1 minus p. So essentially, Q is just the probability of the other side of a coin. So if I have a coin, say I draw a head, and the other side of the coin, let's say I draw a little beagle tail, right? It's a little beagle tail. If, let's say our coin is biased, and let's say it's 3/4 for a head. So this just means the probability of a tail is 1/4. So this Q in our case, our P would be 3/4, and our Q would be 1/4. So this Q is really just P 1 minus P. The reason I use this Q right here is just because if you start looking around on the internet or you look in some statistical textbooks, you'll see the PQ, and Q is just a common representation of 1 minus P. But our textbook and for our course, I believe we'll be using P times 1 minus P, but I just didn't want you to be too confused. Okay. So then here, we then assume that since the variance right here is going to be P of 1 minus P, and we know that the standard deviation, right, the variance is equal to sigma squared, right, which represents the variance. So standard deviation, of course, is the square root of that, right? So naively, what we want to put, we would put n here because that n is going to come essentially from the idea of a sampling distribution. And naively, we would put P times 1 minus P. But this is wrong. And the reason this is wrong is because we don't know what P is, right? We've only estimated it. And in particular, when we're doing these tests, we actually are assuming that the true value of P is P naught. So when we do this test statistic, we actually use our null hypothesis, right? So that's what this is actually is P naught times 1 over n. Okay. And that's just because our null hypothesis is that P naught. Now the P naught, you're going to watch out. You're going to have to watch out in later videos because a lot of times people want to assume P naught is equal to 0. If we're testing for something to be fair, a common mistake that students want to make is that P naught is 0. But you can't do that because if we make P naught equal to 0, then the denominator turns to 0, which we all know results in a lot of mathematical contradictions. So generally, you'll actually find your null hypothesis, and this is not always the case. This is just generally what happens. You'll find that your null hypothesis ends up being 1/2. And now, before I end up finishing off this video, the last thing I wanted to mention is why this is a z, okay? So this question of why isn't it like a p or something? Why isn't it a p-test? Z equals p½ minus p squared. Okay. And the question may be, why z? So why? Okay. This comes from the central limit theorem. And this is a theorem we mentioned a long time ago. This is that theorem we mentioned a long time ago in about, I think, chapter 10, actually. I think it's in the same chapter as sampling distribution. And essentially it says that if we subtract the mean of a sum of random variables and we divide by the standard error and let n tend to infinity, we're going to get a standard normal distribution. So if we suppose n is sufficiently large, n tends to infinity, then we can use a z-table. So the table you'd be using to conduct your hypothesis test is a z-table, and that's why we're using z. Okay, and that's about it. Bye.